Alright, so this is chapter 13, section 7, so 13.7. Starts on page 427 in your book, and it's talking about the viscosity of a liquid, and we defined that in the beginning of these videos, but just as a reminder, generally the viscosity is like the thickness of a liquid, right, and its ability to flow or not flow, and so generally we think of things that ooze or have a very high thickness as being highly viscous, okay, and so this would be things like syrup or magma, lava, anything toothpaste that has kind of a thickness to it and doesn't flow as readily as, say, water or alcohol might, would be classified as things more viscous. And viscosity is an important thing because most of the liquids in our world have some kind of viscosity, and this is a good thing. We want them to have it. But it changes what we've learned about how things flow through tubes, and how pressure might react differently as well. And so when we look at these, which one of these would be the more viscous material? Right? And if you're thinking the one on the right, then you're absolutely right. It's thicker, it flows more slowly, and so we see the same thing in pipes. Whereas so far we've assumed zero viscosity, and zero viscosity doesn't require any net force to be acting on that. However, with a viscous liquid, what we see is that we actually need a pressure differential in order for that thing to flow. And so a simple question, right, would be which of these is easier to drink through a straw, a milkshake or water? And absolutely, the answer is water, because water is less viscous. And we've all probably had that experience of if you get the really good milkshakes, right? You have to pull really hard on that straw to get anything through, and it has to do with the thickness of the liquid that you're trying to pull through, the viscosity of that liquid. Coming over here, right, this is just a zoomed in version of a straw and how a straw works. Even though you've been using straws your whole life, I bet you never considered the mathematical implications of a straw. And so your mouth goes on the low pressure end and you create a low pressure zone in that straw. We call the area at the end of the straw the high pressure zone. It's not really high pressure, but it does have a greater pressure than what you're pulling on the straw with. And so you create this low pressure zone with your mouth, and that causes the fluid to flow through the straw. And so a couple of terms here. We've got the velocity of the fluid, right? The change in pressure, delta P, is going to be the high pressure minus the low pressure equals delta P. Okay, and that's what's coming up here. And so we can actually figure out either the pressure differential that is needed to make a liquid flow at a certain rate, or we can figure out, if we're given the average velocity of a liquid and we know the kind of straw or pipe or whatever it may be that it's flowing through, we can find the pressure differential at each side of that tube. This N here, right, is a Greek letter, and this is the coefficient of viscosity. And obviously, things like water are going to have a much lower coefficient of viscosity, leading to a lower pressure differential to make that flow. The coefficient of viscosity for each liquid differs with the viscosity of that liquid. So a higher coefficient is going to indicate like a thicker liquid. And if you turn to page 428 in your book, up in the top left corner, you actually see those coefficients of viscosity for normal liquids, common liquids in our lives. The nice thing about that table that we see is that it gives it a viscosity of different liquids at different temperatures. And so we know, for instance, that if I have a sample of honey, right, and I've got that at a very warm temperature, then those molecules are going to have a little more action. We also know just generally from life experience that if I warm honey up, it has a much better probability of flowing at an easy rate, right? It's easier to get out of the container than if I've had a jar of honey sitting in the fridge, right? And so when I have things at a hotter temperature, we see a lower viscosity. right? And what we're going to call that is the coefficient of viscosity N. When I cool things off, those molecules get a little bit closer together, and so a lower or colder temperature would lead to a higher viscosity or coefficient of N, right? And when you look at this table, I like the example of honey a lot because it's something that we're very familiar with. Most people have dealt with. And so honey at a temperature of 15 degrees Celsius has a coefficient of viscosity of 600, right? But if I actually warm that same honey up to 40 degrees Celsius, it's got a coefficient of viscosity of 20, which makes a big difference. And so when you're trying to get that honey out of the jar, heat it up, it's got a lower viscosity at that point. And so the other implication of viscosity as it flows through things is kind of an interesting one. And so what I've got here for you in red is a tube or a straw or a pipe of some sort. Viscous liquids, however, actually experience friction against the walls of that pipe. And so you can think of, the walls kind of pushing back on that liquid as it flows along. Now this force is only exerted right at the wall of that pipe or straw or whatever it may be. And so what we see is that the velocity of the liquid as it flows through that is not uniform. And so the velocity of that liquid is greatest at the center because it's experiencing very little friction from the outside of that tube. The velocity right on the edge of the tube, we're actually going to say is 0. It kind of sticks to that. But then from there, the velocities increase as you move towards the center of that tube. If you've ever seen a video of like magma flowing or anything like that, you know that kind of the outside cools, right, and moves very slowly, but the inside is what continually pushes that magma flow forward. And that's because of this principle that with a viscous liquid, the center has the greatest velocity. And so knowing this, we can actually rearrange that little formula that we've already talked about with our milkshake, and we can find, instead of the pressure differential, if we know the pressure differential, we can find the average velocity of that liquid. And so the average velocity of that liquid is equal to the radius squared. That would be the radius of the pipe or the straw or whatever it may be. And 8 times the coefficient of viscosity times the length, and then all of that times the change in pressure. And so remember, we've got like a low pressure zone here and a high pressure zone here that is causing that viscous liquid to flow in the first place. If given these variables, then I am able to calculate the average velocity. Again, know that the velocity is not uniform, but the average movement of these particles, right? All right, and so a really great example of, why we would need to know the change in pressure, why we would need to know the velocity of a liquid is blood in our own bodies. And so I've got this example for you. What is the average velocity of whole blood at body temperature flowing through a 15 centimeter long artery that has a radius of 1 centimeter if the change in pressure is equal to 1600 pascals? And so what I'm trying to find is the average velocity of that blood. And so let's go ahead and do that. We've got the average velocity of the blood. I don't know that. I do know that the radius of that artery is 0.01 meters squared. I'm going to put that over 8. And then the coefficient of viscosity for whole blood can be found in that table on page 428. A whole blood at body temperature has a coefficient of viscosity of 2.5 times 10 to the negative third. And then I need the length of that artery, which is 15 centimeters. I'm going to put that at 0.15 meters. And the change in pressure at that time is 1600 pascals, which is average blood pressure. We usually measure that in millimeters of mercury or inches of mercury in the States. And so when I actually do those calculations, I get that the blood in that artery has a speed, an average speed, remember, because it's a viscosity, an average speed of 53.33 meters per second. Okay, and the last important property of viscous liquids that is important for us to know, besides the pressure differential needed, and besides the velocity at which they flow, is the same thing that we calculated for other liquids, non-viscous liquids, which is the flow rate Q. Now I use Q with a little line through it to indicate flow rate, so I don't get that confused with my heat symbol. And so the Q, we know, for non-viscous liquids is the velocity times the area, and we've already been through that. But in this case, with a viscous liquid, I'm going to talk about the average velocity times the area. And so I already know that the average velocity is equal to r squared over 8 times the coefficient of viscosity, length of the tube or straw, whatever it may be, and the pressure differential. I now need to times that by the area, and area of a circle is pi r squared. When I do that, and there we go, radius squared. When I do that, right, the formula that you see in your book is the simplified version of that. And so we're going to go ahead and combine these two radii because we don't need two separate terms for it. It's the same thing. And so what we see is that the flow rate, which is equal to the average velocity times the area, is equal to pi radius to the 4th power, because we've combined these two. The change in pressure, all over 8 coefficient of velocity times the length. So another good example of application of Poiseuille's equation would be, so we've got a pipe that's carrying 60 degrees Celsius water at a speed of 6 meters per second, and it dumps that water into a nearby lake. If the pipe is 80 meters long and has a radius of 0.63 meters, how much greater than atmospheric pressure is the pressure at the source of the pipe? And so what I'm looking for here is how much greater is the pressure than atmospheric pressure. And so I'm just going to draw a little picture of what I've got going on here. I've got a pipe, right, and there's some pressure here, pressure initial, and then the final pressure is atmospheric pressure, and so it's dropping that water into a lake. The pipe itself is 80 meters long, has a radius of 63 centimeters, and the velocity of the water coming out of here is 6 meters per second. And so what I can do is I can find the change in pressure is equal to 8 pi coefficient of viscosity, length of the tube, velocity average, over, and then pi r squared for the area of that pipe. The nice thing here is that these pi's actually cancel. I don't even have to factor them into my equation. And so I wind up with 8 times, and then the coefficient for water at 60 degrees Celsius is, 5 times 10 to the negative third. The pipe is 80 meters long, water's flowing at 6 meters a second, and it's got a radius of 0.63, which I'm going to need to square. Once I work out all of that math, I should know that the pressure at this end of the pipe is 483.75 pascals, and that's without sig figs. And so knowing that and knowing these 3 equations about viscous liquids, I want you to go ahead and try number 38 on page 435, okay? And then we will see you in class.